Hey folks, we're starting day 11. We're looking at linear recurrence relations still. Let's go ahead and get started. Last time we defined what a recurrence relation was, and this is just a review from that time. It's a formula that defines a sequence in terms of previous values of the sequence. We have this requirement that the recursion formula starts at a certain point for some positive integer, and that we may have to have a certain number of base cases before that recursive formula kicks in. When we want to de-recursify, is that a word? De-recursify a recurrence relation, we use the characteristic equation for that. The characteristic polynomial is what we get when we change the a's to alphas and the subscripts into powers. If roots are real and distinct, we can find a closed form solution to the recurrence relation. And we did an example of this last time, but we'll do another example of it on the next slide. Let's look at this example. We want to solve this recurrence relation. 5an minus 1 minus 4an minus 2 with a naught equal to 2, a1 equal to 5. Let's calculate a couple more of these just so we've got them. A2 is going to be then 5 times 5, which is 25, minus 4 times 2 is 8. 25 minus 8 is 17. And let's do one more. A3 is 5 times 17 is 85, minus 4 times 5 is 20. 85 minus 20 is 65. Okay? So this is growing relatively fast here. And let's see what we can do. The characteristic polynomial, the characteristic polynomial is alpha to the n power equals 5 alpha to the n minus 1 power minus 4 alpha to the n minus 2 power. We'll bring everything to the same side, and this becomes negative 5 alpha to the n minus 1, and then positive 4 alpha to the n minus 2 equals 0. I can factor out alpha to the n minus 2, and I'm left with alpha squared minus 5 alpha plus 4. And that factors into alpha, minus 1 times alpha minus 4. And so my non-zero roots are alpha equals 1 and alpha equals 4. So that's my first step. I write the characteristic polynomial and I set it equal to 0. I solve it. And now we know that the structure is that a sub n is equal to some constant times 1 to the n plus some constant times 4 to the n, which simplifies to just c1 plus c2 times 4 to the n. We'll pick a couple of test cases here. Let's use a1 and a2, for example. When we use n equals 1, then 5 is equal to c1 plus 4c2. It's 4 to the 1 times c2. And when n equals 2, 17 is equal to c1 plus 4 squared is 16c2. If I subtract the bottom equation minus the top equation, 17 minus 5 is 12. The c1's cancel, and I'm left with 12 equals 12c2. And so c2 has to equal 1. But if c2 is equal to 1, then we can go back to this equation here and get 5 is equal to c1 plus 4 times 1. And so c1 is also 1. And so now that I know that C2 is 1 and C1 is 1, my final answer is going to be that A sub n is equal to 1 plus 1 times 4 to the n. And we can see now that that's working. 4 to the first is 4 plus 1 is 5. 4 squared is 16 plus 1 is 17. 4 cubed is 64 plus 1 is 65. 4 to the 0 is 1 plus 1 is 2. I mean, this works for all of our test cases and would continue to work. And so we now have a non-recursive form for this recurrence relation. Okay? So we did some examples like this last time. Then if we have a repeated root, we have to make a modification to one of the terms of our structure, and that's going to give us a slightly different form for this answer. And so if we solve this recurrence relation, an equals 2an minus 1 minus an minus 2, the characteristic polynomial is going to be alpha to the n equals 2 alpha to the n minus 1 minus alpha to the n minus 2. If I bring everything to one side, then I can factor out alpha n minus 2. And that leaves me with alpha squared minus 2 alpha plus 1 equals 0. But this factors into alpha minus 1 times alpha minus 1. All right, so my repeated roots are 1 and 1 here. And then 0 is also a root. And so my structure normally would be that a sub n is equal to c1 times 1 to the n plus c2 times 1 to the n. But these terms are identical, so there's no way to distinguish c1 and c2. That's going to create a problem with linear independence if we try to solve this system. And so we put an extra n right here. All right. So now let's see what happens here. We look at a couple of cases here. A naught is equal to 2. A1 is equal to 2. Something weird happens when we go to A2. 2 times 2 minus 2 is also 2. A sub 3 is 2 times 2 minus 2 is also 2. It looks like all of these terms are going to equal 2. That would be interesting, but let's see how this works out. If we try the n equals 1 case, then we get 2 is equal to c1 times 1 to the 1 plus c2 times 1 times 1 to the 1. And if we look at the n equals 2 case, we get 2 equals c1 times 1 squared plus 2c2 times 1 squared. All right, if I do this again, bottom minus top, two minus 2 is 0. C1 minus C1 is 0. 2C2 minus C2 is C2. And so C2 is equal to 0. But if C2 is equal to 0, then C1 has to equal 2. And so my solution is that a sub n is equal to 2. 2 times 1 to the n plus 0 n times 1 to the n. Just simplifies to just 2. And so the sequence is constant. All right. So then we have one more case we want to look at for recurrence relations, and that's what happens if the roots are complex. If they're complex, they occur in conjugate pairs. That is, if a plus bi is a root, then a minus bi is also a root. Now, this next formula looks complicated, but here's the idea. If I have a complex root like square root of 3 plus I, then a is square root of 3 and b is 1. That's square root of 3 plus 1i. If I plot this, square root of 3 and 1, I have a point that's a certain distance from the origin. The radius out to that point is just a Pythagorean theorem. It's the square root of 3 squared plus 1 squared is 2. Now, if I want to find this angle, the angle is part of this right triangle right here, where the opposite side is 1 and the adjacent side is square root of 3. And so if the opposite side is 1 and the adjacent side is square root of 3, well, that's the same thing as saying that the tangent of the angle is 1 over the square root of 3. And 1 is b and square root of 3 is a. So the tangent of the angle is equal to b over a. That's what we're getting there. And then we can solve that, use that to solve for theta. Theta turns out to be 30 degrees or pi over 6. If we convert a and b from these coefficients into a radius and an angle, then we can write a solution in what's called polar form using c1 times the radius to the power times the cosine of the angle times n, and then c2 times r to the n times the sine of the angle times n. So let's try an example of this. I want to start with this formula here, and let's look at the example on the next page. So the formula was c1 r to the n cosine of n theta plus c2 r to the n sine of n theta. All right. And here's our pattern. It's an interesting pattern, I think. A0 is 1, A1 is 2. But then when we go to A2, it's AN minus 1 minus AN minus 2. So that's 2 minus 1. Goes back down to 1. And then A3, 1 minus 2 is negative 1. And then A4 is negative 2. It's negative 1 minus 1. But then when we get to A5, negative 2 minus 1 is negative 1 again. And then magically at A6, negative 1 minus negative 2 turns out to be positive 1. And so we have this sequence here where the number starts to go up from 1 to 2, and then it goes negative down to negative 2, and now it comes back up positive to 1 again. That sounds like an oscillating pattern, which would be great for a trig function here, like cosine or sine. And that's an indication that we probably are on the right track. So let's see what's going on here. The structure, well, first of all, let's look at the characteristic. Is going to be from right here, alpha to the n equals alpha to the n minus 1 minus alpha to the n minus 2. Bring everything to one side. And subtract 0, subtracting we get equal to 0. Take out the alpha to the n minus 2, and we're left with alpha squared minus alpha plus 1. This doesn't factor nicely, but if we use the quadratic formula, alpha is going to be equal to negative b, which is 1, plus or minus the square root of b squared, which is 1 again, minus 4 times 1 times 1. So minus 4 over 2a, which turns out to be 1/2 plus or minus the square root of negative 3 over 2, or 1/2 plus or minus square root of 3 over 2i. Okay? Now we can convert this into polar by looking at the point 1/2. That's the real part. And then square root of 3 over 2. And we're going to look at this point here. The radius is the square root of 1/2 squared plus the square root of 3 over 2 squared. And we did not have any rain that time, so we don't have any radius that time, sorry. What am I saying? The radius isn't 0, it's 1. It's the unit circle. Bear with me. But we're not getting a radius bigger than 1. It's just 1 unit here. And the angle is, well, if you recognize 1/2 and square root of 3 over 2, this is a 30, 60, 90 right triangle with this angle being 60 degrees or pi over 3. And so the angle is pi over 3. And that tells me that the structure of my solution is alpha, not alpha, a sub n is equal to c1 times 1 to the n, this is my radius, times the cosine of pi over 3 times n. Plus c2 times 1 to the n times the sine of pi over 3 times n. And we need to pick 2 test cases to try to solve this with. And so what I'm going to look at for my test cases, I've got to look at a sub 1, so n equals 1. That's going to give me a sub 1 is 2 is equal to c1 times 1. 1 to the n doesn't really make any difference here. Times the cosine of pi over 3. And the cosine of pi over 3 is 1/2. Plus c2, and then the sine of pi over 3 times 1 is square root of 3 over 2. And that equals 2. And then the other case, let's look for one where this is going to cancel out. Yeah, 2 is fine. When n equals 2, we have a 1 here. And then we have c1 times the cosine of pi over 3 times 2. Well, the cosine of pi over 3 times 2, 2 pi over 3 is on the other side of the x-axis. And the cosine in this case is negative 1/2. Plus c2. But the sine is still square root of 3 over 2. All right, if we add these, we get 3 is equal to, these terms cancel each other out. Square root of 3 over 2 and square root of 3 over 2, if I add them together, is just square root of 3 c2. And so c2 is going to be 3 over root 3, which is the same thing as if I multiply by root 3 over root 3, it's just equal to root 3. And then, now that I know what C2 is, I can go back and solve for C1. So 2, let me change colors for this step. 2 is equal to C1 times 1/2 plus square root of 3 times square root of 3 is just 3/2. But in order for 2 to equal C1 times 1/2 plus 3/2, C1 is just going to equal to 1. And so my final answer is that A sub n is equal to 1 times cosine of pi over 3 n, and then plus C2, which is square root of 3 times the sine of pi over 3 n. All right. Y'all take care. I'll see you again on Wednesday.